A revolution is about to break out because scientists at the European Centre for Nuclear Research, or CERN, have restarted their cosmic gun, the Large Hadron Collider. In light of recent advancement in the rekindled ambitions of particle physicists, the grand game of discovering the nature of the cosmos has therefore begun. The collider had been generating signs that the universe might be concealing something amazing even before it underwent its renovation. What is the origin of the universe, and why does it contain matter as opposed to antimatter? Join us as we explore how physicists at CERN just made an incredible discovery that changes everything. A decade ago, CERN physicists made headlines around the world when they found the Higgs boson, a long-sought-after particle that gives the rest of the cosmos its mass. But what is still missing? Almost everything, according to optimist physicists. The universe was up for grabs in 2010 when the CERN Collider was first turned on. The Higgs boson was the target of the largest and most potent machine ever built, the Standard Model, a system of equations that explains everything researchers have been able to measure about the subatomic realm is built on this particle. But the Standard Model falls short in explaining some more fundamental issues with the universe, like its origin, what it composes, and even why the Higgs particle itself has mass. Scientists are hopeful that recent discoveries will shed light on the mysteries surrounding dark matter and other open-ended issues in science. There is a lot about dark matter that we don't know. That most matter in the cosmos is truly invisible to us is a startling revelation. Because they can detect the gravitational signatures of dark matter, astronomers assume that it must exist. The invisible cosmic framework known as dark matter is what holds galaxies and galaxy clusters together. We don't know exactly what it is, though. Dark matter is for sure one of the most intriguing scientific puzzles. When the Big Collider was turned on for the first time in 2010, physicists believed that some solutions might emerge. But except for the Higgs, nothing else was discovered, especially no novel particle that would shed light on the composition of dark matter. Unfortunately, the Standard Model was unaffected. At the end of 2018, the Collider was shut down for substantial improvements and maintenance. The Collider will operate until 2025, at which point it will shut down for another 2 years to allow for the installation of other significant modifications. Improvements to the enormous detectors that sit at the 4 locations where the proton beams clash and examine the collision debris are included in this round of upgrades. Those detectors have been put to the test since July. Squeezing the proton beams increases the likelihood of protons colliding at the crossing locations, but it also confuses detectors and computers since there are several sprays of particles that must be differentiated from one another. Various experiments in the meantime have indicated potential flaws in the Standard Model and suggested a more comprehensive, in-depth view of the cosmos. These findings concern unusual actions of subatomic particles, whose names are unknown to most of us in the cosmic stance. Consider the muon, a subatomic particle that achieved momentary fame last year. Muons, which have the same negative electrical charge as electrons but are 207 times more massive, are frequently referred to as fat electrons. Nobody is sure how muons fit into the whole picture. They are produced during collider events and by cosmic ray collisions, and they decay radioactively into a fizz of electrons and spectral neutrinos in just a few microseconds. 200 physicists from the Fermi National Accelerator Laboratory in Illinois discovered that muons spinning in a magnetic field wobbled much more quickly than the Standard Model predicted. This discovery was made public last year. The difference between experimental results and theoretical expectations appeared in the value of a parameter termed G2, which characterized how the particle reacts to a magnetic field at the 8th decimal point. The quantum whisper of as-yet unknown particles that would temporarily form around the muon and change its properties was attributed by scientists as the cause of the little but significant variation. The Standard Model would finally be broken if the existence of the particles could be confirmed. For investigating nature at the smallest scales, the Higgs boson functions as both a strong telescope and a very precise microscope. It has access to very high-energy scale physics. Because it wants to decay to lower energy, a truer vacuum, physicists refer to our vacuum as a false vacuum. It's the dips and hills of the Higgs field's energy potential that maintain our universe in this imaginary vacuum long enough for planets, stars, and galaxies to form. However, this false vacuum is inherently unstable and will deteriorate over time. Quantum energy fluctuations, or the peculiar quantum tunneling phenomena, may enable the fake vacuum to penetrate the energy barrier, allowing it to traverse those hills and roll down the slope on the other side. Everything would be destroyed and replaced with a true vacuum as a result of the disintegration of the fake vacuum, which would spread outward in a wave moving at the speed of light. Whatever happens, it wouldn't be good for the cosmos. Since only the Higgs field is preventing vacuum decay, we should therefore be grateful for the current cosmos. So here is yet another attempt to understand the universe. These models are essential to the Hadron Collider's endeavor to find physics that goes beyond the standard model. The standard model of particle physics, despite its many achievements, is by no means the last word on the matter. It does not, for instance, suit cosmological models that explain the origin of the universe. However, while they wait for more evidence from the Fermilab experiment, two groups of theorists are still trying to match up their predictions of what G2 should be. Another anomaly also involves the muon, one of the 6 types of quarks that makes up heavier particles like protons and neutrons. The B quark is the main character, or possibly the antagonist in this story. These quarks are found in the 2-quark B meson particle. However, due to their instability and propensity to disintegrate, these quarks appear to defy the standard model. A daisy chain of events may be involved in some uncommon decays of a B quark, leading to the production of a new lighter quark and a pair of light particles known as leptons, which may be electrons or their fat relatives, muons, or both. According to the standard model, the likelihood of both electrons and muons appearing in this process is equal. The tau is a third heavier lepton, but it decays too quickly to be seen. However, Dr. Patel and his associates have discovered more electron couples than muon pairs, defying the lepton universality principle. This anomaly, like the muon's magnetic anomaly, hints at an unknown influencer, a particle or force interfering with the reaction. One of the most dramatic possibilities, if these data hold up in the upcoming Collider run, Dr. Patel says, is a subatomic speculation called a leptoquark. If the particle is real, it might close the gap between the 2 types of particles that make up the material universe: quark-based protons and neutrons, and lighter leptons like electrons, muons, and neutrinos. There are enticingly 6 different lepton types and 6 different quark types. Dr. Patel stated, "We are entering this run with more optimism that there may be a revolution coming. Fingers are crossed." The W boson, which carries the so-called weak force responsible for radioactive decay, is another particle in this menagerie acting strangely. The Collider detector at Fermilab, or CDF, reported on a 10-year effort to measure the mass of this particle in May. The effort was based on approximately 4 million W bosons collected from collisions in Fermilab's Tevatron, which was the most potent collider in the world prior to the construction of the Large Hadron Collider. The W boson should weigh roughly 80 billion electron volts, the preferred measure of mass energy based on the standard model and earlier mass measurements. The Higgs boson, in contrast, weighs 125 billion electron volts, or roughly the same as an iodine atom. However, the WCDF measurement, the most accurate measurement ever, came in at 80.433 billion, which was higher than expected. According to the experimenter's 7 sigma calculation, there was only a 1 in 2 trillion chance that this divergence was a statistical fluke. There is a relationship between the mass of the W boson and the masses of other particles, including the infamous Higgs. Therefore, if this latest discrepancy holds up, the standard model may have another flaw. The 3 anomalies may all disappear with further information, as could the revolutionaries' hopes. However, all 3 indicate undiscovered particles or forces that interfere with known physics, which is heartening to optimists. As a result, Kyle Cranmer, a physicist at the University of Wisconsin who participates in other CERN investigations, suggested that a new particle that might explain both G2 and the W mass might be discovered at the LHC. Therefore, even while the LHC won't shred the fabric of time and space, it might help researchers lift the curtain on some of the universe's mysteries. The LHC will be used by researchers to examine the Higgs particles' more delicate interactions and look for evidence of the elusive dark matter, which makes up roughly 27% of the universe's matter, but which has never been directly seen. Let us know what you think of this discovery in the comments section below.